Greetings! Today we're going to discuss kinetics and the collision theory. Well, take a look at this picture. Are we talking about collision as in this type of collision? Not really. We are discussing collision of molecules to form other molecules, like in a chemical reaction. Before we start our discussion of collisions, let's talk about kinetics. Kinetics is the study of rates of chemical reactions, rates of reaction. It comes from an ancient Greek word, kinesis, which means movement or to move. What does this mean? We start out with reactants and we form products. We have already discussed chemical reactions. But the rate at which reactants disappear and form products, that's the kind of reaction rate that we're talking about. How fast does this process take place? The collision theory actually has three postulates, or it has three parts. It has to do with how particles collide with each other. First of all, in order for these reactions to take place, particles, molecules must collide with each other. They have to collide with each other with sufficient energy. And thirdly, they have to have the correct orientation. So let's say that molecules can only react in this way. If they collide with sufficient, but they collide with sufficient energy and their orientation is this way, the reaction will not occur. They will only bond together when they react in this way. So you can see that there are several things that must happen in order for these reactions to take place. Collisions are the easy part. Do they have enough energy to form these bonds or to break these bonds? And do they have the correct orientation? Are they aligned properly? Those are important factors to consider. Let's draw a little picture of how these reactions work. Let's say that we're reacting fluorine gas and nitrogen dioxide. Let us say that we have F2 and this is F2. And they are bonded together, okay? I should have drawn them a little closer. And that we have N with two oxygens attached. Oxygen and oxygen. This is the correct orientation. If fluorine approaches the NO2 in this orientation, the reaction will take place. However, if it approaches from this direction, the reaction will not take place. So they have to collide. These two must collide. These two must be aligned in this manner and must have the correct amount of energy required. Now let's discuss activation energy. Activation energy is the minimum amount of energy that is required for a chemical reaction to take place. So in this diagram, you can see that we have energy, and down here we would have the progression of the reaction. Okay? So this is R. Here we have the progression of the reaction. So here's what's happening. Here we are showing the reactants. We start out with the reactants, and they must collide, and they create what's called an activated complex. This is right before the reactants disappear and the products appear. So right before that moment. And then the reaction proceeds and energy is dropping down. Notice that the products have less energy than the reactants had initially. We'll discuss this at a much later date, but for now, I just want to show you a couple of things. Number one, this is called the activation energy. In other words, the amount of energy that it takes for the reactants for these collisions to take place and the reactant to reach this point at which we have an activated complex. I'm going to move on and talk about what happens when you have a catalyst in place. But that is at a much later, in the next podcast. Why is this important? In order to understand reactions, we need to understand how the progression of energy occurs. In order to understand these reactions, so that we can understand what catalysts do. Catalysts speed up the rate of reactions. And we're going to see that a little later in another podcast.
Now we're going to talk about the factors that affect the rate of a reaction. But we have to always keep in mind the collision theory, and it's because of its importance. Now, any factor that increases the rate of successful collisions will affect the rate of reaction. Any factor at all that increases the collisions will affect the rate of reaction. Let's think about this. I want you to pause, think, and write down all of your ideas. How can we increase the rate of collisions or the number of collisions when we are trying to react to substances or more? While you're thinking, I'm going to go over to the lab, get things ready, and show you how you can increase the rate of collisions. But first, pause and think for yourself. So here we are in the lab, and I want to tell you about how you can actually increase the rate of a reaction by doing very simple things. All right, number one, we're going to talk about temperature. Now let's talk about hydrogen peroxide, H2O2. Very simple compound. We can decompose it easily by just letting it sit here. I can open up this bottle and let it sit here, and eventually it will decompose. All right. But if I wanted it to decompose a little faster, I could possibly put it on my hot plate, heat it up. What have I done? Effectively, I will increase the collisions by making the particles move faster as I heat them up. You know this from experience, that eventually substances boil and there's an increase in the collisions because the particles are moving faster, so the chances of collisions are much greater. An example to that would be if you go to a dance and it's a large hall or fairly large hall, and you only have 10 couples. Well, the chances of them colliding is going to be very, very small. But if they start dancing kind of crazy, there may be a kind of a chance that they will collide. But we're going to get back to that example in a moment. All right, so if I heat this up, the decomposition is going to take place, and it's going to be a lot faster because those collisions are taking place. All right, secondly, we could increase the concentration. So instead of using H2O2, I could use H2O2 30%. This is 3%, this is 30%. So I can increase the concentration and cause a reaction to go along a lot faster. And that helps quite a bit. Thirdly, what could you do? Use a catalyst. And a catalyst is simply, we're going to discuss it a little later, but it's simply a substance that speeds up the rate of a chemical reaction. So I'm going to put some hydrogen peroxide in here, and I'm going to add a catalyst as soon as I have a spatula to be able to put that, manganese dioxide into that container. Right back. So here we are. I have my spatula, and I'm going to add some manganese dioxide. And it's starting to fizz a little bit, and you can see it's rising. So there's a reaction taking place in this test tube. All right, so I can add a catalyst for this decomposition reaction that has already started. Here it is, it's bubbling. It's hard to see from where you are, but I'm going to bring it close. It's bubbling quite a bit, and it is decomposing as we speak because of the catalyst. Now, in class later, I will show you how 30% reacts when I increase the concentration and use a catalyst as well. There's one more way to increase the rate of a reaction in the case that we're using a solid. Say I'm using a solid right here, copper sulfate crystals, and I want a reaction, not this reaction, a different reaction, to take place quickly. If I just put these crystals in the container where the reaction is taking place, the collisions can only occur around the crystal. But since I want this reaction to have more surface area, instead of just using these crystals, I'm going to go ahead and crush them so that I'm increasing the surface area where these collisions can be increased. So there you have it. We can either increase the temperature, we can increase the concentration, make the solution more concentrated so that there's more particles. The more particles, getting back to my example, if you're in the dance hall and now instead of 10 couples, you have 300 couples. Now the chances of collision are going to be greater. So the same here for greater concentration. Using a catalyst will also increase the rate of the reaction. And finally, we can increase or change the physical state so that you can actually increase the surface area where the particles will hit in the case of a solid. Okay, there you have it. See you later. Now I'd like you to reflect on your ideas. How did your ideas compare with the answers given? Have a great day.